we find out that for vibrational motion, there's two components. There's a kinetic energy component and a potential energy. We saw in at least a barrier, I'll throw this one out at you. When we did this, and we had a particle incident on that barrier, we discovered tunneling. We discovered that there is a finite probability that the particle will appear on the other side of that barrier. Part of it has to do because it is a wave distribution. We draw it like this, but it's a quantum wave. And so there's a potential to get to the other side. That was a quantum mechanical tunneling effect. So you had to have a barrier. Is there any quantum mechanical tunneling in rotation? Very subtle question. I like the book. Is there any tunneling in rotation?
If there's a barrier for it to be in certain angles, maybe?
There has to be a barrier. And so far we have no barrier to rotate. It was free rotating. So there is no tunneling. There's no tunneling problem that comes within that. Anytime you have a potential energy, then you have a potential, no pun intended there, to tunnel. So rotation didn't have it. Translation only did because we had a finite barrier. What would be the tunneling if this barrier were infinite? What would be the probability of being over on that side? This goes back to the question when we did this problem here. We did there. When we did this problem, similar to the particle Moravec problem, the wave function over here was 0. It could not exist because it had an infinite potential there. So it cannot tunnel. It cannot exist in that region. It was 0 here. It was non-zero here, just as when this is a finite barrier, it's non-zero within here. If it is an infinite barrier, forget it. You don't have enough energy to get in there. So there's no tunneling effect. What we did over here is, in this system, we made sure that the wave function in this region at 0 was equal to the wave function in region 2 at 0. And it had to be 0. Not so over here. Here we find we have a wave and we have actually a decreasing probability within that barrier region. And so instead of setting it equal to 0, as we did over here, we just said that sine region 2 is at A, we call that A, is equal to sine region 3 at A, and the derivatives. Those were our boundary conditions, because we allowed the possibility that the wave function can exist in this region because it is a non-infinite region. So the finite infinite factor really comes into play here. But now, like I say, we've got two energy components. I do have a potential energy, so we're going to find there will be tunneling probabilities in vibration. So let's take a look at the systems here. So we finished off this slide. I just gave the classical result that we would observe. And classically, the particle can stretch, it can contract, but at its turning points, they slow down, comes to a rest briefly, and then reverses itself. So it spends most of its time at the end, very, very little time in the middle. So now, what does the quantum mechanics say? Before I do that, there's going to be a couple of problems that we've got to contend with. The first being that in this model, as the particle stretches, the potential goes up and just keep going up, keep going up, keep going. In other words, the potential energy, if I have this X, and this is the potential energy, looks like this. So here is the RE, the equilibrium bond distance. As it stretches, the energy goes up, 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 up. And over here, I compress it, the energy goes up, 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 up. The question is, does this reflect a real molecule? Well, it doesn't, because if I take a real molecule and I continue to stretch it, eventually the bond breaks. So a real molecule is not represented by this particular curve. It is most represented by the curves we looked at in the past, one representing like a Morse potential here. So this is the harmonic potential. It just keeps going up. Molecule never dissociates. But in a more realistic, remember that the Morse potential was an empirical. It was made up, and we parameterized it. However, later, very soon, after we get through with the quantum statistics, we'll build molecules, and we'll be able to reproduce those curves, but we'll do it quantum mechanically. However, in a Morse empirical model, as the molecule stretches, the energy flattens out and finally goes to flatline. In other words, the molecule has become dissociated. As the molecule contracts, the energy tends to go up a little higher than it does with a potential model. So this then possesses somewhat of a problem. On average, does a molecule behave more like a harmonic or more like a Morse? Well, if the molecule is vibrating down here, then the harmonic model will work perfectly. If the molecule is vibrating up here, then we're going to get a lot of error. Secondly, that there's this problem that we're going to have, particularly with spectroscopy, of the fact that if a molecule is rotating, if it stretches, by a conservation of momentum, the rotation slows. As it contracts, it speeds up. So you have this slow, speed, slow, and that's called vibrational rotational coupling. In that instance, we have to ask the same question. If the molecule is vibrating up here, we're going back and forth and back, and you think about it as kind of a gravity well or something, and going back and forth here, well, that vibrational rotational coupling is going to be a problem. If the molecule is vibrating down here, then our rigid rotor approximation will turn out to give us very, very good answers. So that is a question that has yet to be answered. So we'll take a look into that, but we have to be wary of that sort of thing.
How would you treat a molecule that has vibrational and rotational coupling?
What we will find actually, not tomorrow, but if everybody's back a week from Tuesday, right? Yeah, so we're gonna meet in here a week from Tuesday, and we're gonna talk about that very thing. So what we're gonna end up doing, and near the end of this set of notes in here, you'll see how we address that. Right, but that is an answer definitely coming. Definitely coming. Yes?
So if your vibration's higher up on the graph, there's more and more air.
More.
If you get way up there at the very top of the graph.
So we're up in here.
Yeah, there's air.
More error, yes. I thought I said air. So is that if you're saying error? Yes, that's correct.
As you keep going up, you're going to get more air.
So it could possibly be, if molecules just vibrating down here, okay, we'd be okay. Things will work. What we will run into, and this is what we're going to talk about a week from tomorrow, is that when we do spectroscopy, we're deliberately exciting molecules to higher states, incorporating more of the error that you're pointing out exactly correctly. So how we're going to deal with it is forthcoming. I was just hidden as kind of a secret, just keep you on the edge of your seat before then. But yes, you're right.
Those are bond distances, right?
Correct. So in this particular molecule, the equilibrium bond distance, this was for, I think, hydrogen H2. So I picked that. So the equilibrium bond distance was 0.7416 angstroms. The dissociation energy is about 4.5 EVs. So the distance from here to the bottom is the bond energy. That's how much energy you have to put in to break it. And the equilibrium bond distance is that 0.74, which is for hydrogen.
And does mass affect this, the graph?
Does the mass?
Yeah, like for hydrogen it's like this, but it's like this for every other.
Yes, it does. And it does through the reduced mass. If you recall that the frequency is 1 over 2 pi root k over mu. That mu, that reduced mass. So that's, by the way, if I had hydrogen and deuterium, they're going to be, and we will look at this, someone's going to do this, and when you do the HCl spectrum in the laboratory. In that particular instance, we're going to look not only at HCl, but DCl. The D is going to double that reduced mass, and it's going to shift that frequency way over. So yes, it does. It does play quite a dramatic effect on that. Okay, wonderful. All right, so now the quantum mechanical solution running. Again, this is one of those differential equations that we're not going to want to solve. It's a series solution, just as it was with the rigid rotor system. In this system, we have kinetic energy term minus h bar squared over 2 mu now. We're in a center of mass coordinate system. But the potential energy is now 1/2 kx squared. That k, by the way, then governs this curvature here. So if it's a very, very high k, very stiff bond, this thing is going to contract up, and you'll get, instead of something that looks like this, for a large force constant, K, you might get something like this. Well, imagine now a ball rolling back and forth in here. The ball is on this curve, it goes back and forth, but in here it's going to go more quickly, higher frequency, and along that line. So the K is then related directly to that. All right, just as in the rigid rotor system, we will also see in the hydrogen atom, the solutions, the wave function to the harmonic oscillator are a set of polynomials. These ones are called the Hermite polynomials, and that's called Hermite's differential equation. Again, we will not solve it. It's very algorithmic, and we just simply produce the answers. So the wave function is a normalization constant given here, where I have this alpha over pi. Alpha is a square root of k mu over h bar squared. We'll examine that a little bit further. And so alpha over pi to the 1/4 power, and the only thing that varies is the square root of 2 to the n is your quantum number. The Hermite polynomial, it is given, just like in the rotator, it's given in terms of a variable x or z or something along that lines. But the argument of those Hermite polynomials are actually the square root of alpha times x, where x is the distance, again, from the equilibrium bond. So there's your alpha, there's your n, and the quantum numbers in there. And it is also interesting to note that the energy of a harmonic oscillator system is your quantum number n. N equals 0 now is allowed. We could not have an n equals 0 for a particle in the box, because that would imply that the particle was at rest. And you can't have a particle at rest, it's a violation of the uncertainty principle. Because we can't know exactly where it is. If it's at rest, we know exactly where it is, we know exactly how fast it's going. That's a violation, you can't have that in a wave. However, in a vibrating molecule, the n equals 0 is allowed. If this is 0, your energy is 1/2 h mu 0, which is its vibrational frequency, and that's called 0-point energy. Bottom line is, that's why, one of the reasons why it is impossible to get to absolute 0. You can't get to 0 Kelvin ever, because there's always a vibration taking place. This result here is what Max Planck, Einstein, and then had to conclude in order to solve some of the problems, like the black body radiation and the electron ejection from metals. So what they had to do is to imply that there is a fixed set of vibrations. They just didn't know why. But here the quantum mechanics just said, it just popped out very, very naturally. So there again, there's a frequency system like that. All right, so we look at classical systems. They look like this. Let's go to quantum systems, see what it looks like. So the Hermite polynomial, before we do that, there is a homework problem that does this, so let's take a look at one of these. Here are the Hermite polynomials, and again, these are given in terms of z, but when you apply it to the harmonic oscillator, the z is the square root of alpha times x. So these are just another set of polynomials, and as I did for the rigid rotor, I just kind of present for you all kind of the generating functions, the mathematics that goes along with that. This we will need later. Here we're going to do today, I'll show you that one. So these are derivatives, and this is a generating, or what is known as a recursion relation. This is going to be, when we get to spectroscopy, we're going to need that very badly, so we'll come back to that. But this says if I have an Hn and an n-1, I can get the n+1. So let's take a look at that. I had you generate, I think in homework, I think I had you generate this function from the previous two. But an example that I have here, and by the way, they are mutually orthogonal, which is a good example there. So here's one where I have an H3, and I'm going to generate the H3, and then use H3 and H2 to generate H4. This will kind of bootstrap our way up. And it's really fairly easy to do. And like I said, I have one of your homework problems, I actually have you do that. It's not a difficult issue. But if I want to generate H3, again, I'll just make this in terms of, I'll call it Z. I have an X here. But this is -1 now to the third power, that's the 3. Now I have to take 3 derivatives. I'll use Z. I'm inconsistent here because I put Z's in here, but I put an X here. That should be a Z within there, so that. 3 derivatives of e to the minus z squared, and then that whole thing, once I'm done with that, is multiplied by e to the positive z squared. That's where that goes. So if I take 3 derivatives of this, it's simple. The d dz, derivative of that is minus 2z, then you get e to the minus z squared again. Do it again. The second derivative with respect to z squared becomes this first times the derivative of the second, so this becomes equal to, now I have a 4z squared, e to the minus z squared, then plus, or now minus 2. So that would be the second derivative, doing this again. The third one, and this is all e to the minus z squared as well. So the third derivative then gets us our polynomial. So doing this a third time, and that one again, I will take. I'm gonna make this 4z squared minus 2 times e to the minus z squared. I just factored out the e to the minus z squared. So that was my second derivative. The third one, again, it's the first times the derivative of the second, so I have minus 2z now times 4z squared minus 2. And that will be multiplied by e to the minus z squared. And then plus, that's going to be 8z, then all of this times e to the minus z squared. So I can just put that all together. This becomes now a negative 8z cubed plus 4z plus 8z all times e to the minus z squared. So that takes my derivatives. Now it says take negative 1 to the third power, which is at negative 1. So this, if I now do h3 of z, this becomes, that's 8, 4, that's 12z. So all the signs change. So it becomes 8z cubed minus 12z. And then it says multiply by e to the positive z squared. That takes that away, and so that is the result. And that's what we have. I think I got that down here. So yeah, we have 8z cubed minus 12z. Well, then we can use the recursion relation. I said, now this is h3, h2 of z is, where did I put that up there? It's 4z squared minus 2. So now, this is going to be, have you ever heard of the term selection rules? Inspector again? Okay, we'll get to that. That's where we're going to be this. That's why I'm kind of going ahead and just doing one of these. So if I wanted now an h4 of z, this says, see, here's hn plus 1, so I'm going to bring these two here to the other side. So it's going to be, it said it's going to be equal to 2z times h3 minus 2 times 3 times h2. We follow that. So h4, just rewriting that, is going to be 2z h3 of z, and then minus 6 times h2 of z. If I just kind of follow that recursion.
How did that formula on here?
I just grabbed H2. I didn't generate it. I generated H3. I just grabbed H2 from that table. And now I'm going to use that recursion to generate H4. That's all I'm doing there. So we have our H3, so it becomes 2Z now times 8Z cubed minus 12Z, so that's this term here, and then minus 6 times H2, which I just got, again, from the table, of 4Z squared minus 2. So now it's just the algebra. So I have 16Z cubed, then minus 24Z squared, and this becomes minus then 24Z squared plus 12, or 16Z cubed minus 48Z squared. Is that right?
1604.
Thank you. Thank you. Yes, you're absolutely correct. I just see if you're watching. So nice catch. And I think that's what we have after. So again, we're going to use these later, so I wanted to at least do it once, just so you can see before we get around to that. All right, now it's time to ask some questions. Things I want to know is, where is the oscillator most likely to be found? That goes back to this question of this curve right here. Is it low or is it high? We need to know that. Also for vibrational rotational coupling. Then I want to know, what is the average position? Now, it's pretty obvious. What will be observed macroscopically, and what kind of energy storage might be. And all that would be the statistical mechanics that we come into. Because
When would we use the When would we use them?
you hear me, polynomials?
Polynomials, yeah.
You heard me, polynomials? We would use them to generate the wave functions, and then once we have the wave functions generated, then we can do all our standard quantum mechanics and averages and stuff. But we're using them to produce the wave.
For wave functions for vibrational molecules?
Mhm.
Okay, alright.
Yeah, that's correct. You use the Legendre polynomials for the rotor, and later we'll have another one.
And so rigid rotor is different than rotational, or rigid rotor is rotational, right?
Rigid is rotational, yes.
Okay.
And the question is that a reasonable assumption to take for something that's rotating? Can we reasonably say that the bond length is fixed when we produce the wave function? Because if the molecule's vibrating like this, then that rigid rotor approximation is going to go down the tubes.
Don't they all have to correspond to each other too, each and every state, translational, rotational, and
Mhm.
vibrational?
Yeah.
Like, where is that point where they become from translational goes to rotational, rotational goes to vibrational? Because now we're just examining different points in quantum, right? We have 3 different
Mhm.
states. But how would you know when is what? How would you treat a system as such?
All molecules will have all 3 motions. And so what we will do is, when we want to examine a particular type of motion, maybe the center of mass motion around the room, we'll try to use the wave functions for translation. What Lena and I were talking about earlier, the difference between translation and rotation and vibration at the same time. In rotation, you have a fixed point, that center of mass. So a pure rotation, a molecule, that point does not move. So it rotates this way, but it's a center point. Same thing for a pure vibration. In a pure vibration, the center of mass does not move. Just molecules oscillate, with that. And so we could always, thank goodness for the center of mass coordinate system, we could always break up those motions and examine them individually. So that works. But yeah, they're all there, but we're just examining one at a time, and we can combine them later as we need. Okay? All right. Yeah.
I'm looking at the H4Z. Where did that equation come from?
Here.
Yeah.
That came from the standard math tables have this right here. So I said n equals 3 in this example. So that's 3. That's 3 plus 1 or 4. That's 3 minus 1 or 2. What I did is I took these 2 terms, brought them over to this other side. So it became on one side 2ZH3 minus 2 times 3H2. That's where I got that. And later we'll do that in general, and we'll see where that's going to come out. It's very, very, very useful. Well, tons of information will come out of it. All right, so what I did is I grabbed a hydrogen fluoride molecule, treating it as a harmonic oscillator. If I go look up the fundamental vibrational wave number, notice this. You typically look up frequencies as wave numbers. That gives you their vibrational wave number. To get it into a frequency, I multiply by the speed of light. So this is reciprocal centimeters times centimeters per second gives me reciprocal seconds, which is then a frequency. For a HF molecule, the dissociation energy is about 428,000 joules per mole, or 428 kilojoules per mole. And of course, I popped it into joules by just dropping the Avogadro's number. The reduced mass, I used the hydrogen times 19. I just kind of got close. And the hydrogen, so mass 1 times mass 2 divided by mass 1 plus mass 2 in grams per mole. And of course, I have to get it in absolute kilograms. Then the force constant, just defining from the frequency, is then produced there and out. So I was just kind of doing a little bit of the algebraic work there. If I take it now and ask, what does the wave function look like? I took advantage of MathCAD built-in Hermite polynomial function. It's built in, it has this HER, capital HER, then you have an argument. This is which one it is, first one, second one, third one, or whatever. And then we have the square root of alpha x, that of course is the argument of this. So MathCAD has it built in, I can use it. The normalization constant I pulled up from upstairs, it's right there, and we always have this e to the minus alpha x squared too. So there's the wave function generated. I'm going to plot it from minus 1.5 angstroms to plus 1.5 angstroms, and I have the quantum state set at n equals 0, the ground state. When I plot it, we have ourselves a little bit of a situation. Because classically, we know part of that vibrating thing spend most of the time at the turning points. Quantum mechanics says diametrically opposed. It says, nope, it spends most of its time in the middle, very little time at its turning points, which we have yet to establish and define. So again, we're running into this problem is the classical doesn't agree with quantum mechanical. The proposed solution to that is the Born, or the correspondence principle, rather. The correspondence principle says you make your system heavy enough, more classical, it should turn into a classical system. Well, we can do that by simply increasing the energy. That's why I put this in general. So let's now look at the n equal 1 quantum state. So now it's one energy state higher. Well, now it kind of splits, which is interesting. Now we have a 0 probability in the middle, which is kind of the same as a particle in the box problem. How does it get from that vibration to that vibration? But if I continue this, let me do an n equal 10. For an n equal 10, you can see what's happening. Now we're getting, I don't know how much MathCAD will allow me to go on this, but you can see as we're getting in higher and higher and higher and higher energy states, we're now beginning to approach the classical model. So once again, the correspondence principle is correct. It says, all right, we are raising weight, we're raising energies, and we're approaching the classical model. But the question still remains. Is it in the n equal 20 quantum state? Is it in the n equal 0 quantum state? Is it the n equal 200 quantum state? Which one is it in? We have yet to establish that. In doing this, let's look at some average values. I will do 1, and then I have one completely outlined here. I will do 1, and then there's one for the homework that was done. We'll get to that another time, because that's end of the week or something along that line. But the average position, we have an advantage in the harmonic oscillator system because the limits are, all space for the vibrator are minus infinity to positive infinity. I know it's kind of an odd thing to consider that it closes to minus infinity, but we have that as a symmetrical limit. Whenever I have a symmetrical limit, I'm getting all bubbly inside because I'm looking at the integrand. If an integrand in a symmetrical limit is odd, the integral is 0, end of story. I don't have to do any more work at all. So for the x average, going from minus infinity, this is a wave function squared multiplied by x. Well, x is odd. You go to negative x's, it's negative. You go to positive x's, it's positive. So this is an odd integrand integrated over symmetrical limits. So I can say without question, the integral is 0. All the negative and positive values cancel out. The average square distribution is a little bit more challenging, but I have it here. I'm not going to go through it all, but first, this one I can do easily. Let me do one. The challenging, what I meant challenging, it's challenging if you do it in general. I can do it fairly easily for the ground state. So let me grab the ground state wave function. So psi 0 of x is alpha over pi to the 1/4 power. The Hermite polynomial for the 0 is 1. So it just ends up being e to the minus alpha x squared over 2. So that is the n equals 0 quantum state. If I want to find the average square, again, I'm applying the same principles we had in chapter 11. Reintroduce those things. This is going to be then alpha over pi, now square root, because that's squared, integral from minus infinity to positive infinity, now of e to the minus alpha x squared over 2, the wave function, times the operator x squared, that's what I'm looking for there, and the wave function again, e to the minus alpha x squared over 2 dx. So that's everything, we're just doing the same thing all over again. So we're just applying that. Collecting the terms, I can now do this, I can call it 2 times the square root of alpha over pi, because this now becomes 1/4 becomes a square root. Just times the 0 to infinity of x squared e to the minus alpha x squared dx. The operator for positions is multiplying. So there is a Gaussian style of integral from 0 to infinity, which tells me to go immediately, do not pass go, do not collect $200, go to the set of integrals for the Gaussian type of functions that we've seen before. This one is an even, it's x squared, where n is 1. So e to the minus, that b, of course, is our alpha. So just following that, I get this 2 root alpha over pi. Then I have 1 times 3 times 5, all the way to 2 times 1 minus 1. Well, 2 times 1 minus 1 is 1. So the numerator just becomes 1. The denominator is 2 to the 1 plus 1, or squared. Fourth, I have alpha, and then the square root of pi over alpha. The pi over alpha and alpha over pi go away. This ends up being 1 over 2 alpha. So that is the average square. It's easily done on just the ground state or any other particular state. In general, the average square is actually n plus 1/2. And this is 1 over alpha, it's 1 over 2 alpha. Alpha is the square root of kdu over h bar squared. So that produces that as your general value.
What is the average square distribution of? Is it just the distance where it is?
Yes. But instead of saying average distance, the average distance has both positive and negative values. An average square has only positive values. So it gives a measure of its average deviation from its equilibrium position. And that's why when we did the average square deviation, what we did is we took a value minus the average, squared it. Remember doing that? That's almost like we do a standard deviation. That then defined for us the uncertainty, what we call. So the uncertainty in x is average x minus the average squared, but when we had analyzed this before, it came out to be this. Is the average squared x minus the average x squared. And that was actually the square root of all that. So that's what it ended up being. So when I want to find this deviation, what I'm about to do is just demonstrate the Heisenberg uncertainty principle. We have this average square, which is that value there. Then we have the average edge, which is 0 squared, and that'll give us the uncertainty, or it's kind of spread in its spacing. By momentum arguments, you could make the same argument that the average momentum, it has not going one side or the other, but to any preference, because it's a harmonic model, then you can just argue that the average momentum is 0. Down here, I won't do this, but here is how this yellow x average in general is done. What I do is I have Hermite polynomials, I have an x squared, I have to do a transformation, and then this is the recursion relation from up above. So I use that, collecting, again, I'm not going to do it, I just wanted to have it here so you just have a sense of completeness. So we get our average x squared, we get that particular type of result. So then here's what I just mentioned, the uncertainty. So the uncertainty in x is then the average x squared minus the average squared, square root, which is then the result we just produced. The average momentum, again, by symmetry is 0, and this just argues that. In this argument, I do a couple of things. Here is this odd integrand over symmetrical limits, so that's 0. And then in doing this, I needed to take, for a momentum, I needed to take a derivative. Well, I used the derivative relation from up above to get the derivative. And when I do that, again, this is just for illustrative purposes only, but when I do that, I get an integral that looks like this. I have psi n minus 1. They are all orthogonal, so I don't need to go on. I know that is 0. Hermitian operators kind of come back and benefit us again. So then there is the average square momentum, so the uncertainty, now this is the Heisenberg uncertainty principle, the uncertainty in the x multiplied by the uncertainty in the px must be greater than or equal to h bar over 2, and in fact, for delta x, delta px, we get n plus a half h bar, so at its very lowest energy, then it is equal to h bar over 2, and every time I increase the quantum numbers to 2, 3, 4, the uncertainty is still satisfied. So all the quantum mechanics comes in, and they're all satisfied within here. So I just wanted to kind of go through that just to show how these are generated. I won't have you do that. All right, now we get back to that question again. What is the fraction of the bond length is the root mean square average? This is a question that's asking, is it doing this or is it doing this? Is the average a large fraction of its bond length or a very small fraction? To do that, I get my HCl parameters here. HCl has an equilibrium bond distance, 127.46. It has a vibrational wave number, 2989.7 reciprocal centimeters. And once again, I get the frequency by simply multiplying by the speed of light. Giving all the other parameters then put into place. There's my mass 1 and mass 2 and reduced mass. And so what I do is calculate then, here is from above, this is the root mean square average, in other words, the uncertainty. The bond length is RE, so if I take the uncertainty, kind of a measure how it's stretching, divided by the bond length, it comes out to less than 6%. That's good news. That means if I have a bond length here, then at its very worst, it's vibrating around only about 6% of its bond length. That means it's not doing this. That means those curves I had up above, we're feeling a little bit better about using a harmonic model.
So if it was a higher percentage, then it just doesn't fit the graph?
Right, then if it is a higher percentage, then you're going to get up into what Francis pointed out about the error. This is right here. So we find that we are, at least as far as the stretch goes, down here. If it were a bigger percentage, if it were 100%, just take that 75 and 100% of that, you'd be up here. We'll get all here, and all here is going to incur a lot of error.
So like, would 100 be all the way up?
Which one?
Would 100%, if you were to have 100% of
Well, listen, this one has a bond length of about 0.75. So 100% of that would be 1.5. That's what my back. So that would be about here. So it'd be stretching about here to here. And so we would incorporate a lot of error. All right, now, again, with the spectroscopy, though, we will be pumping molecules up into here.
So we'll have to deal with it. But that tells us that for your average molecule getting values, then we're going to be in a pretty good place. Now, what about this vibrational rotational coupling problem? Now we're feeling pretty good about that too. Because again, if it's vibrating widely, as it contracts, it's going to speed up. As it stretches, it's going to slow down. So what I calculated here is what is kind of the spread of the moment of inertia. The moment of inertia was the determiner of the vibrational rotational frequency. So we find that for this particular molecule, I just took the difference or divided by the average of the error essentially. I get about 11%. So your moment of inertia I, remember that the energy was J plus 1 h bar squared over 2I. The more variance there is in that number, the less accurate this will be. We're finding the variance of that number is maxed at about 11%. And actually for heavier particles, it actually goes down. I picked a weak one. I picked a very, sensitive molecule. So that means that the moment of inertia is not changing. There is some coupling and vibration rotation, but it is not significant. But again, that is in the ground state. We'll have to deal with that at another time when we do a spectroscopy on that. All right, so good news. We're down in the bottom of the well. The harmonic model will work. Then finally, here's the question of thermal conditions, but always the question I have to ask, because ultimately we're going to put this together at 300 Kelvin to find out what all these averages are, the internal energies, entropies, and enthalpies, and all that. So I have to ask the question like I asked for the last two systems. On average, is the molecule in high quantum states, medium quantum states, or low quantum states? Well, again, I picked my thermal temperature to be kT, so I set my energy, 1 n plus a half h nu naught equal to kT, solve for n, and I get an n on average of just slightly above 0, which tells us at 300 Kelvin, particles are in their ground state. That's why this heat capacity of 3n minus 5r term was so bad. It was horrible because this presumed that all vibrational frequencies are thermally active and available, that I can store energy there. Well, that says not a chance. You cannot store energy as vibration thermally unless you get extremely hot. I will put strict numbers on that. All right, so translationally, we're very high quantum states. Rotationally, we're somewhere in the middle ground. The heavier the particle, the better. Vibrationally, we're in the basement. And the model I always use in my baby bee cameras, of course, is trying to heat up a molecule. I use an analogy of having these 4 water tanks. I said we're going to add energy, and we'll take the energy in terms of filling this tank with water. If this is translational, rotational, and vibrational, and if this is just an atom, I add water, the tank fills fairly rapidly. That's the temperature going up. If the molecule can rotate, there's a little shunt here, and it's low. So if I fill this with water, then some of the water is going to be distributed, the energy is going to be distributed around the molecule a little bit more, and so both tanks go up in temperature fairly slow. And then we always came to this. In this instance, our shunt is way up here. So it's not until you get the temperature way up here before you can start utilizing that. So that's why that term was so bad. So now we have a fundamental theory that tells us why that's the case. What we're going to do about it is the stat method. We'll be getting into that. All right, the last thing we'll do this. Well, there's a couple more things to do. We'll come back the next time to do this. But again, now in our system we have a potential energy. The molecule could stretch. Is there then a significant probability that the particle will stretch beyond its capable energy levels? That will be an important process. So think about something like this. Think about maybe a proton exchange, a potential energy for a proton, and some of you are going to be doing this, calculating this in the laboratory. So here is maybe a proton exchange. So you have a proton over here, And you have to raise the energy to get the proton away from one particle to put it over to the other. So maybe, you know, like an H3O plus and an H2O, and you want to swap a proton. Well, there's an energy barrier to that, which looks like this. Well, it turns out, and some of you are going to do this for ammonia. Ammonia has this, of course, C3VE symmetry, but it can also flip, where it kind of does an inverted umbrella type of thing, where it can do that. And the plot, or the potential current, looks like this. Well, there is a barrier to that, and it turns out that quantum mechanically you can actually tunnel through that barrier. So the rate at which protons are exchanged, or the rates at which these are inverted, are faster than what we expect. And actually, you can actually see that in an infrared. There's two very small little peaks in an infrared spectrum of ammonia that actually show exactly what that is. So we're going to find out, okay, how much does that do? How much tunneling is there in this particular system? So we'll take care of that in next time. Fascinating stuff. You know I like it. Well, I think I talked about all the homeworks, haven't we? If we just have 6. We'd have 6 homeworks. And then on Wednesday, I'll talk about the first 2 binaries.